Today we're going to dive into something that's like a secret language for your brain. It's the grammar of clear thinking, logic and set notation. Now don't worry, this isn't about some kind of scary math. It's about learning a language that lets you build rock-solid arguments and, maybe even more importantly, spot the shaky ones from a mile away. Think of it as a toolkit for clarity.
You know that feeling, right? You're in a discussion, maybe a debate, and it feels like you're both just talking past each other, arguing in circles. You're using the same words, but they seem to mean completely different things. It's so frustrating. Well, that happens because our everyday language is honestly a bit messy. Today, we're going to get the tools to just slice right through all that fog. So here's the game plan. First, we'll learn the basic alphabet of logic. Then, we'll figure out the rules of the road with something called truth tables. After that, we are going to tackle the trickiest, most misunderstood phrase in any argument, the if-then statement. From there, we'll check out a much more visual way to group ideas using sets. And finally, we'll pull back the curtain and see how these two languages, well, they're basically two sides of the very same coin.
All right, let's jump in. Section 1, the language of logic. So, instead of A, B, C, we've only got a few key symbols to learn. But trust me, with just these symbols, we can construct ideas that are incredibly powerful and, most importantly, have zero ambiguity. This is where we lay the foundation.
Okay, so the building blocks here are actually super simple. We take a basic statement, like it is raining, and we just give it a label, P. Simple enough. The real magic, though, happens with the operators, the logical and, or, and not. These are like the glue that lets us connect all our simple P's and Q's into a much more complex, much more interesting logical sentence.
Okay, so if logic is a language, then truth tables are its grammar book. They're basically our cheat sheet. They tell us, black and white, whether a complex sentence we've built is true or false, just by looking at whether its little pieces are true or false.
Take a look at this table. The AND column is pretty much what you'd expect, right? P and Q is only true if both P and Q are true. Makes sense. But look over at the OR column. This is where things get interesting. In logic, P or Q is true if P is true, or if Q is true, or if both are true. Now, this is a really big deal. In real life, if someone asks, do you want coffee or tea, you're expected to pick one, not both. But logic is more precise. It's inclusive. And that little difference is key.
And now, for the main event, the implies operator. This is what creates those famous if-then statements. Now, this rule has a really weird quirk, so stick with me. An if P then Q statement is only considered false in one specific situation, when the if part is true, but the then part is false. Think about it. If it rains, then the ground gets wet. That sentence is only a lie if it does rain and the ground somehow stays bone dry. But here's the twist. If the if part is false, if it doesn't rain, we consider the entire statement to be true, no matter what the ground does. It's called being vacuously true, and believe me, it trips people up constantly.
Which brings us right to the heart of what we're talking about today, the if-then trap. This single concept is where so many arguments, so many debates just completely go off the rails, all because we think we understand how these statements work, but we really don't.
So let's start with a nice, simple statement that we all learned in geometry class and we know is true. If a quadrilateral is a rectangle, then it has two pairs of parallel sides. P implies Q. No arguments there. That is a solid, true statement. Now here's the mistake pretty much everyone makes. We assume that if P implies Q is true, then if we just flip it around, that must be true too. Well, this flipped version, if Q then P, actually has a name. It's called the converse.
Okay, so let's look at the converse of our nice, safe geometry statement. If a quadrilateral has two parallel sides, then it is a rectangle. I mean, that sounds pretty plausible, right? It feels like it should be true, but is it?
Nope, it's false, and that is the trap, right there. Why? Can you think of a shape? How about a parallelogram? A parallelogram has two pairs of parallel sides, but it's not always a rectangle. We found just one counterexample where the if part was true, but the then part was false, and in logic, that's all it takes to blow the whole thing up. This is a classic logical fallacy, assuming the converse is true.
So, if just flipping it is wrong, is there a right way to rephrase an if-then statement? Oh, you bet there is. It's called the contrapositive. Here's how it works. You flip the statements and you negate them both. So for our example, it would be, If a quadrilateral does not have two pairs of parallel sides, then it is not a rectangle. And that statement is absolutely 100% true. The original statement and its contrapositive are logical twins. If one is true, the other is guaranteed to be true.
Okay, let's totally switch gears for a minute. We've been talking about logic using words and statements. Now let's explore a parallel language that's way more visual. Let's talk about set theory. This is really all about just grouping stuff together.
So the most basic idea is just a set. It's a collection of things, like numbers or people or whatever. We can have subsets, which is where one whole set fits inside another one. And just like in logic, we have operators. Intersection is where you find the stuff that's in both sets, and union is where you combine everything from either set into one big group. Starting to sound a little familiar?
And now, we get to the final piece of the puzzle. This is the moment where we see that logic and sets, they're not really two different things at all. They're just two different languages trying to describe the exact same ideas.
And here it is. This is the big aha moment. The logical operator AND is the exact same concept as the set operator intersection. They're both just about finding the overlap. And the logical OR is the exact same thing as the set union. They're both about combining everything. One is a sentence, the other is a picture, but the core idea is exactly the same.
So what can we actually do with all this? Well, we now have this awesome thinker's toolkit. First, the power move, modus ponens. If you know if P then Q is true, and you can prove that P is true, boom, you've just proven Q. Then there's the defensive move, modus tollens. That's using the contrapositive. If you know the then part is false, you can prove the if part must be false too. And finally, you can build logical chains. If P leads to Q and Q leads to R, then you've just built an unbreakable bridge all the way from P to R.
See, in the end, logic isn't just some abstract thing for a classroom. It's a really practical tool for building better arguments, for spotting bad ones, and for just getting your ideas across with power and precision. It really is the grammar of clear thinking. So the real question is, now that you have the tools to see the hidden structure beneath all our messy, everyday language, what are you going to build with them?